Hi friends, let us see another type of Butterworth filter design problem. In this problem, the characteristics are given in terms of decibel units. So there are some changes in the regular procedure of solving the Butterworth filters with decibel units characteristics. Let us see what the problem is. The problem given for today is an IIR LPF is required to meet the following specification. Passband edge is 1.2 kHz, passband peak to peak ripple is less than equal to 1 dB, stopband attenuation is greater than equal to 40 dB, stopband edge is 2.5 kHz, sample rate is 8 kHz. So if I draw this characteristics again similar to that of the previous one, then I have on the x-axis my omega, I have on the y-axis my h of e raised to j omega. Now the problem over here is the passband edge frequency and the stopband edge frequency are in the kilohertz. So first we need to convert them to the digital frequency. So to convert them to digital frequency, I will write as omega p, which is equal to 2 pi fp by fs, and omega s is equal to 2 pi fs by f, let's make it fst. FST stands for sampling frequency because we have an fs over here term again. Fs stands for stopband frequency, st stands for sampling frequency. Okay, or you can reverse the things. You can make this fst and keep this as fs. That will also do the job. Now the values that we'll get out of this is 0.94 and 1.96. So omega p that I am getting out of this is 0.94, and here I am getting omega s as 1.96. Magnitude remains the same whether it is analog or digital. So I have the stopband attenuation greater than equal to 40 dB, and the passband attenuation is this is my 1 scale, so this will be my passband edge frequency. So the passband edge AP is given as 1 dB less than equal to 1 dB. This is AS, which is equal to 40 dB, and my maxima now, my maxima will be 0 dB. Okay, why this is 0 dB? We are taking the absolute scale or the normal scale. If we don't take decibel scales, if suppose, then the maximum value was 1 that the filter can attain. That was this line, that is 1. So if I take log to the base 10 of 1, then I am going to get 0. And how we calculate decibels? We calculate decibel as 10 log to the base 10 of 1. So 1 multiplied by 0 multiplied by 10 will give me 0. So I will have the maximum value as 0 dB. This will be actually minus 1 dB, and this will be minus 40 dB. That means 40 dB down from the maxima. And the characteristics will look like, it will have the characteristics like this. So it will attain 0.94 at 1 dB, and it will attain 40 dB at 1.96. So these are the digital characteristics of a low pass filter. This is how the low pass filter looks like. Now we need to find the analog domain characteristics of this low pass filter. So we need to find step 1, that is the analog filter characteristics. And in analog filter characteristics, I have AP as 1 dB, AS as 40 dB, omega P is 0.94 and omega S as 1.96. Now I want omega P, which I can calculate using 2 by T tan of omega P by 2, and we can calculate omega S, which is 2 by T tan of omega S by 2. And if you solve this, you are going to get 8.13 radians per second, and if you solve this, it will be 23.85 radians per second. Here you don't assume T to be 1. Why? Because the sampling frequency to us is given as, or the sample rate is given as 8 kilohertz, right? So if you use that, then Ts will be equal to 1 upon Fs, which is our 1 upon, which is T, that will be 1 upon 8 kilohertz. Okay, if you put 1 upon, it will go up, it will become 16 kilohertz. So you will get kilo radians per second and kilo radians per second with this K into consideration. Okay, so that are the two values of omega P and omega S. You got all the characteristics of a analog filter. Now you have to find the order of the filter. So step 2, obtain order of filter. So we get order of filter as n, which is greater than or equal to 1 by 2. It was like this, log to the base 10. Initially I used to write 1 upon as square minus 1 divided by 1 upon ap square minus 1, the whole divided by log to the base 10 omega s by omega p, right? In this formula, AS and AP are not in decibels, but now in current problem they are in decibels. So we need to modify this formula according to decibels or convert the decibel into normal values. So we know that AS in decibel can be written as 10 log to the base 10 of normal value AS, right? So if I wanted to find a normal value AS, then I will have a normal value AS will be equal to AS in decibel divided by 10, and let's say log to the base 10 over here. AS in decibel divided by 10. So this is in decibel. I am writing this line to show that it is in decibel. So AS in decibel upon 10, dividing both sides by 10. Taking antilog is 10 raised to on this side. So the normal AS will be equal to 10 on to the power AS in decibels divided by 10. Now 10 AS in decibel divided by 10 can be written as 0.1 into AS in decibel. Right. Now, as I said that the actual value of AS is minus 40 dB per decade. So either you can put the value over here as minus 40 dB per decade and substitute over here, or we can directly substitute this over there. So the new modified formula for order with decibel scale is n greater than equal to 1 by 2 log to the base 10, okay, 10 raised to 0.1 AS minus 1 divided by 10 raised to 0.1 AP minus 1. This is the new formula for the order of the filter. if you substitute the order of the, if you substitute the values, n comes as somewhere around 4.9, which approximately equal to 5 we have to take. Therefore, the order of the filter is 5. So, this is the only change in the problem. Whenever we get a decibel unit characteristics, the formula for order changes. Rest all procedure remains the same as the other type of Butterworth filter design. That means after order you have to find omega c, that is the cutoff frequency. After finding cutoff frequency, you go for h of s. After finding h of s, you go for h of z. Now, I just wanted to emphasize more on this factor because we have received a negative, odd value of order. So, the h of s will be, this is for odd ordered filter. Numerator remains the same, that is omega c raised to n. In the denominator, you have s plus omega c into continued product of, let us say k equals to 1 to now n minus 1 by 2. Okay, it will be n minus 1 by 2 into s square plus omega c bk, okay, s plus omega c square. Here bk is again similar to that of the previous, is sine 2k minus 1 by 2n of pi. So, this is the only change that you need to take care when you are designing the filter. Here the filter was odd, so the transfer function that you will write is omega c raised to n, the whole divided by s plus omega c, one pole has gone, remaining 4 poles, that will be k is equal to 1 to n minus 1 by 2 s square plus omega c bk s plus omega c square, where bk's are given with this factor. That is the only change that you have to consider when you design a filter with the decibel units. Thank you.